So here's a definite integral where a substitution would be useful. You might think of starting off maybe making u be the natural 1 plus the natural log squared of t. But if you calculate du in this case, let's see, the 2 comes down, you get natural log to 1 power less, and you multiply by the derivative of the inside gives you 1 over t. And while there is a, times dt. While there is a dt over t in the problem, this is a little bit messy because of the ln t. So rather than do that, I'm just going to try just letting u be ln t. That way du is 1 over t dt. And so we'll end up with something that looks like it's going to be an arctan, because we're going to end up with 1 over 1 plus u squared. Good. So in our substitution here, the dt over t, that just becomes du, so we have 4 du, and then we have 1 plus ln squared would be u squared. But I need to figure out what my bounds are. So in order to figure out what my bounds are, I look at the equation that defined my substitution. To get my lower bound, plug in the original lower bound. Now the natural log of 1 is 0, so my new lower bound is 0. And to get the upper bound, plug in the original upper bound. Let's see, the natural log of e to the pi fourths means the exponent you put on e to get e to the pi fourths, and so that is pi fourths. Good. Now I can pull out that constant 4, and I see that this is a function this is an antiderivative I recognize, because the derivative of the arctan is 1 over 1 plus inside squared. So we have 4 times the arctan of u, evaluated between 0 and pi fourths. So we get 4 times the arctan of pi fourths minus 4 times the arctan of 0. And I know the angle whose, let's see, the angle whose tangent is pi fourths. Ooh, that's a little bit tricky. I guess we'll just have to leave it as is. Now let's see, the angle whose tangent is 0, I know is 0, so we end up with 4 times the arctan of pi fourths. Now, there is a way to do this integral without changing the bounds. What you could do without changing the bounds is just forget about the definite integral for a second and focus on finding an antiderivative. You'd make the same substitution. If you let u be ln t, then du is 1 over t dt, and so we get here, our integral becomes again 4 du over 1 plus u squared, and so we recognize this as being 4 times the arctan of u plus c. Since the fundamental theorem says you could use any antiderivative, except for I'll have to substitute back if I'm going to put the bounds in here again. So so if I do it by finding an indefinite integral first, then I'll want to substitute back, and u was the natural log of t. Okay, so, and the fundamental theorem says you just need any antiderivative, so I won't worry about putting the constant in, because I'm doing a definite integral. The constant's going to show up in both the first term and in the one I subtract, and so it's going to go away anyway. Okay, so now that I've found my antiderivative, then I can go back to the original function and say, okay, well, I know what the antiderivative is, so I'll just take that antiderivative, 4 times the arctan of ln t, and evaluate it between my two endpoints, and I'll end up with the same answer. Since the natural log of e to the pi fourths is pi fourths, I'll still get 4 times the arctan of pi fourths minus 4 times the arctan of 0, which is 0. But the thing is, I had to take this little sidestep and work out what it was, and the real waste of time here was substituting back. I was going to have to figure out what the natural log of those bounds was anyways, because it was part of that function. So I might as well just change the bounds and keep moving and then I won't have to substitute back. This will actually save a lot of time, and it's worth learning how to do. We'll need to do it when we have integrals inside of integrals. It'll be much better probably to change the bounds. So get used to changing the bounds. Don't just go this antiderivative route if you can